All right, so the combined gas law is what we're going to talk about here, and it pulls together actually three different laws. It pulls together Boyle's law. So you take Boyle's law, which is P1V1 equals P2V2. It brings in Charles's law. This is V1 over T1 equals V2 over T2, and something called Gay-Lussac's law, which is P1 over T1 is equal to P2 over T2. Now it takes these three and it puts them all together so that we can look at changes in pressure, volume, and temperature all at once, given that we have a constant amount of gas particles. So our moles of gas particles are going to be the same. So here it's all combined. We're going to smush all these together and we're going to get the combined gas law, which is, just as a reminder, at constant moles of a gas. So that's N. And we write it as P1 V1 over T1 is equal to P2 V2 over T2. So maybe you can see how these three fit together, and the relationship holds because we know that pressure and volume are have an inverse relationship, which is what we see. But pressure to temperature and volume to temperature each are direct, and so that's what we see here in this law. So right here, that is the combined gas law. I'm going to show you how to work an example problem using the combined gas law. So let's say that we have a gas in a container. It's at a pressure of 760 millimeters of mercury. So that's our initial pressure. The initial volume is 45 liters, and the initial temperature is 273 kelvins. Now we change the conditions a little bit. Not sure what happened there. Let's do that. Decrease the volume to 35 liters. We increase the temperature to 323 kelvins. And what we're not sure about is then, well, what's our pressure going to be? So we're asking a question that's a little more complex, but using the combined gas law, we can still figure this out. Now in this example, we're going to solve for P2. So I'm going to write that down. P1 V1 over T1 is equal to P2 V2 over T2. And I'm going to solve for P2 here. So I'm going to do a little bit of algebra. So if I multiply both sides by T2 and divide both sides by V2, so I'm going to put T2 on top divided by V2 to match what's over there. So that means that my T2 and my T2 cancel out, and my V2 and my V2 cancel out. So I'm left with P2, which is what I'm trying to do. So I'm going to rewrite it. So P2 is equal to, and now I'm going to just put a little different order here, P1 V1 T2 divided by T1 V2. Okay, I'm ready to plug my numbers in and see where this goes. So I'm going to plug them in, and let's see what happens. So let's make that look a little nicer here. P2 is equal to, let's see, P1 is 760 millimeters of mercury times V1, which is 45 liters, and times T2, which is 323 kelvins. We're going to divide this by 273 kelvins, excuse me, and 35 liters. Now at this point, it'd be really good to check unit cancellations to make sure that you set things up correctly. And that's the magic of units, is they'll tell you if you've made a mistake somewhere along the way. So let's see, my liters are going to cancel out like that. My kelvins cancel out. And look at that. I'm left with millimeters of mercury. And since I'm in pressure, that's what I want. So I think I've set this up correctly, and I'm ready to do this calculation. If I'm punching this into a calculator, like a simple calculator, a scientific one, this is how I would enter it into the calculator. I would type in 760 times 45 equals times 323 equals, and then I would divide by 273, and then hit equals, and then divide by 35 right here, and then equals. I'm very liberal with my use of equals. So if I do this, my pressure calculates to be 1156 millimeters of mercury. I look at this, it's 3 significant figures, and so my P2 is equal to 1.16 times 10 to the third millimeters of mercury. And that is how we use the combined gas law to figure out something a little more complex, where pressure, volume, and temperature are all changing. We can still calculate it. It's just a little bit more cumbersome. If only there was a way to tie these things together, maybe into some sort of gas law that's ideal. Wink, wink.